Swayam Prabha. Digital India. Educated India.
Welcome students to this fourth lecture of week 2 of the NPTEL course Environmental Soil Chemistry, and in this week we are talking about different inorganic components of soil. So, in the previous 3 lectures of this week we have talked about in details about different primary minerals and different types of coordination structures. We have learned about Pauling's rules. We have talked about 5 different Pauling's rules. Then we have talked about different coordination compound, coordination number, and then no rattling limit, and then how this coordination structure changes depending on the ratio of radius ratio of cations and anions. Then we have started talking about primary minerals. I have showed you different examples of primary minerals, and also we have started talking about the secondary minerals. In the secondary minerals, as you know, we have started with 1:1 type of mineral. In the 1:1 type of mineral, we have talked about 1:1 dioctahedral kaolinite. We have discussed their structure, and also we have discussed the halloysite, which has the similar structure as kaolinite, but with an interlayer water molecule. So, today's lecture will be starting with this 1:1 trioctahedral serpentines. Now, in this 1:1 trioctahedral serpentines, they are basically 2 trioctahedral serpentine that are 1:1 type of clay are their most important are antigorite and chrysotile, and these clay have all 3 octahedral position fields with magnesium. Because these are trioctahedral, you know that in the trioctahedral structure 3 out of the 3 octahedral positions are filled, and in that case magnesium is the major cation. So, in this case all 3 octahedral positions are filled by magnesium, and there is no substitution in either the tetrahedral or octahedral sheet, and thus they have no permanent negative charge. The permanent negative charge always develop due to the isomorphous substitution. Whether there is no isomorphous substitution, just like in kaolinite, there will be no negative charge development. Similarly, in case of this 1:1 trioctahedral serpentine, as you can see, I have shown you the picture of antigorite and chrysotile. Both of them don't show any kind of isomorphic substitution. As a result, they are having no permanent negative charge. So, we have completed 1:1 type of clay mineral. Now, let us move to 2:1 type of clays. At first, in the 2:1 type of clay, let us talk about the pyrophyllite talc group. Now, pyrophyllite is a 2:1 dioctahedral clay, and it belongs to this pyrophyllite talc group. So, if you see, it has the chemical formula of this Al2Si4O10OH2, and it does not show any kind of isomorphous substitution. So, this is a characteristic feature of this pyrophyllite, and as a result of that, it is electrically neutral. And since it is electrically neutral, it has the layer charge per half cell formula unit 0. So, it has 0 layer charge per cell formula unit. So, in case of clay mineral, we generally use half cell formula unit to define its chemical composition and layer charge. So, in this case, in case of pyrophyllite, we are having 0 layer charge. So, there is also no interlayer space. However, the edge sides play a major role in various physical properties and retention of metals. So, although they do not have any kind of negative permanent charge development due to the absence of isomorphous substitution, they do play some roles in different various physical and retention, physical properties and retention of metals. So, if we move ahead and see the structure of the pyrophyllite, it is becoming more clear that this is a 2:1 type of structure, as we have discussed. 2 silica tetrahedral sheet and 1 octahedral sheet sandwich in between these 2 tetrahedral sheet, and it is basically a dioctahedral structure because aluminum is present. So, this is the structure of pyrophyllite, and as you can see, among the 2 layers the interlayer space is almost 0. So, this is the structure of pyrophyllite, and this is the actual pyrophyllite mineral. So, let us move ahead and see what is the another important mineral in this group. Another important mineral in this group is talc, which is also a 2:1 trioctahedral clay. So, again it is a trioctahedral clay, that means it has magnesium in its structure. So, as you can see in this chemical formula, magnesium is present, and also it does not show any type of isomorphous substitution, just like as pyrophyllite and interlayer space, and it has also the 0 layer charge per half cell formula unit. However, the edge sides may play a major role in various physical and retention of materials, just like we have seen in case of pyrophyllite. So, let us move ahead and see what are the other important 2:1 type of mineral. Let us discuss the serpentine, smectite serpentine group. This is one of the major, one of the very important group, and this group consists of dioctahedral smectite and trioctahedral saponite, and it has a layer charge of 0.2 to 0.6 per half cell formula unit. Now, an example of this dioctahedral smectite is montmorillonite. It is one of the most important mineral, clay mineral we are going to talk about. And other dioctahedral smectite are beadylite and nuntronite. And as far as the trioctahedral saponites are concerned, the examples are saponite and hectorite. Among all of these, this montmorillonite plays a very important role in soil physical and chemical properties. So, if we move ahead and see in details about the montmorillonite, this montmorillonite clay mineral basically looks like. So, the layer charge basically in case of montmorillonite originates from the substitution of magnesium for aluminum in the octahedral sheet. So, here the mainly isomorphous substitution goes on in the octahedral sheet. It is highly nutrient rich because it generates high negative charge or permanent charge, and it has very high shrink swell capacity. Why we will discuss. That means, this clay can shrink during dehydration, and if you rehydrate that soil, it will swell. So, this is one of the major property of this type of clay mineral. It will shrink and swell. So, it is also very unstable under low pH and high moisture condition. So, if we go ahead and see the structure of montmorillonite, this is the structure of montmorillonite looks like. So, basically if you see, this is one layer, this is one layer, and this is another layer, and in this 2:1 type of layer you can see at the octahedral layer one aluminum, So, basically it is a dioctahedral structure. So, in the dioctahedral structure, when aluminum gets replaced by this magnesium, then this negative charge develops. And in the interlayer space, this interlayer space between two layers is basically occupied by calcium, magnesium and water. So, basically miscellaneous cations and water molecules occupied in the middle, and as a result there is a large gap between the two adjacent layers, and it is that is why it is showing high or maximum swelling. Okay. So, I hope this is now clear to you. If we move ahead and see what is the reason behind that. Now, as I have told you in the last slide that isomorphous substitution occur only in the octahedral sheet, negative charge develops, and when the negative charge develops in the surface of these clay mineral or in surface of these layers, there is always a natural repulsion between the negative charges when the two layers come very close, because similar charge they repel each other. As a result of that, there is a high space in between, and it causes cations to move into the interlayer space where they can be replaced by other cations. So, this is the reason that this Montpellier shows high swell and shrink property. So, this is in details about the structure of the Montpellier. Remember, the d axis spacing is 1 to 2 nanometer. It is highly it is highly expanding type of mineral. So, here the d axis spacing is 1 to 2 nanometer. Now, what is the d axis spacing? D axis spacing is basically the distance between two repeating layers of atoms. So, here if you see, these are two adjacent layers, and in this adjacent layer, if we consider this is the top layer of oxygen, this is the top layer of oxygen. So, the repeating top layer of oxygen will be found here in the next adjacent layer, and this linear distance between these two repeating similar layer of atoms is called the d axis spacing. Now, the d axis spacing is highest, one of the highest in this case, that means in the Montpellierite clay mineral among all the mineral. So, this is the electron microscope view of Montpellierite. You can see it is irregular flake like structure, and the clay in India, which is mostly dominated by this Montpellier type of soil, clay mineral, is the black cotton soil, which you can see in the peninsular region, especially in Maharashtra. So, here you can see this type of soil, and as a result of swelling and shrinkage, this soil looks like this. They basically develop these large cracks during the summer season, where there is no water, and water will be dehydrated from the soil. As a result, there will be large cracks, as you can see. And during the monsoon season, when there will be further water movement, then these cracks will be closed. So, this is called periodic swelling and shrinkage property of Montpellierite. So, other 2:1 type of clay in the smectite saponite groups are badellite, nontronite. So, in case of badellite and nontronite, isomorphous substitution occurs in the tetrahedral sheet. We have seen that in case of Montpellier the isomorphous substitution was occurring in the octahedral sheet. Now, in case of badellite and nontronite, this isomorphous substitution occurs in the tetrahedral sheet. Remember, nontronite is iron rich and saponite is is a mineral where isomorphous substitution occurs in the tetrahedral sheet. Hectorite is basically lithium bearing mineral, and also in case of hectorite, substitution occurs in the octahedral sheet. So, depending upon which particular ion is dominant and where the isomorphous substitution is going on, we can differentiate different types of clay mineral. Another 2:1 type of mineral is mica. Remember, in case of mica, it has a layer charge of 1 per half cell formula unit. It is basically dioctahedral in nature, that means aluminum is dominated in this octahedral sheet. Examples are muscovite and paragonite. Also, there are some trioctahedral micas. Examples are biotite, phlogoptite and lepidoptite. Now, except paragonite, other micas have potassium ions in their interlayer space. This potassium ion is very small and it basically comes in the interlayer space and lock the structure. And as a result, these micas are the major potassium bearing minerals in the soil. When these micas weather, they basically converts into partially expansible 2:1 type of clay like illite and vermiculite. We will be discussing those two clay minerals in the next slides. So, mica is a 2:1 type of clay mineral. It has both dioctahedral and trioctahedral variants, and dioctahedral, one of the major dioctahedral variant is muscovite, whether one of the major trioctahedral variant is biotite. It has got potassium ions in their interlayer space, and as a result it is a major potassium bearing minerals in the soil, and as a result of weathering it can convert into partially expandable or partially expansible 2:1 type of clay like illite and vermiculite. So, this is the structure of muscovite as well as phlogopite. You can see that how these potassium ions are in between these layers. These are the small potassium ions and this is the basically 2:1 type of structure, and this is the phlogopite structure. Now, in case of muscovite, it is basically dioctahedral, and in case of the phlogopite, you can see it is basically trioctahedral structure, since magnesium is present in the octahedral sheet. We have already discussed that in the previous slide. Now, let us move ahead and see another very important mineral called 2:1 type of one of the major important 2:1 type of clay mineral, that is illite. The another name of illite is fine mica. I mean, it is basically a weathered product of the mica, and it has a layer charge of 0.8 per half cell formula unit, which is intermediate between smectite and mica. And just like just like mica, its interlayer space is also dominated by potassium. It is the predominant interlayer ion, and it has more silica, magnesium and water, but less tetrahedral aluminum and potassium and water than mica. As you can see here, there is a structure of the illite. As you can see, this is a 2:1 type of structure, and interlayer space is occupied by potassium, making it a locked and collapsed structure, and here the d axis spacing is only 1 nanometer. So, this is basically in details about the illite structure. The interlayer space is occupied by this potassium ion, and since it is a basically weathered product of mica, it is also known as the fine grained mica. It is non-expanding type of mineral. It shows minimum swelling because of this interlayer potassium ions, which basically collapse the structure, since these potassium ions are very small in size. Now, one of the basic features of this illite structure is the isomorphous substitution always occurs in the tetrahedral sheet. And as a result of this isomorphous substitution in the tetrahedral sheet, K plus or potassium ion comes into the interlayer space to satisfy the charge. So, as a result of tetrahedral substitution, isomorphous substitution, there is negative charge developed in the surface, and this negative charge which develops in the surface is occupied or satisfied by this potassium ions which comes into the interlayers, making it a lock structure. As a result of that, this is illite is basically known as a a non-expandable or minimum swelling type of mineral. So, this is elite electron microscopic picture. You can see it basically appears like fibrous under the electron microscope. Now, another important mineral is vermiculite. Now, vermiculite is basically a weathered product of illite. When illite goes further weathering, it basically converts to vermiculite. So, it is basically a weathered mica product, because mica is the major mineral from where the illite has been formed, and then further down this vermiculite group is formed. So, these are weathered mica products where the potassium ions between the molecular sheets are replaced by magnesium, and so this is the one of the major distinguishing characteristics and difference from illite. So, in the illite, the interlayer space was occupied by potassium ion. However, when further weathering going on, this potassium ion get replaced by water molecules as well as magnesium and other ions. So, there is a dominance of magnesium in the interlayer space in case of vermiculite, and it has a layer charge of 0.6 to 0.9 per half cell formula unit. Dioctahedral vermiculite, obviously you can see the substitution in both the tetrahedral and octahedral sheet. However, in the trioctahedral variants of vermiculite, you will see substitution only in the tetrahedral sheet, and all three of the octahedral cations position are filled by magnesium. So, if we go ahead and see the detailed structure of vermiculite, it becomes very clear that why it is having high negative charge development, because it shows the isomorphous substitution both in the tetrahedral sheet as well as in the octahedral sheet. So, you can see in the tetrahedral sheet silica gets replaced by this aluminum, whereas in the octahedral sheet aluminum gets replaced by magnesium as well as iron. Irons are denoted by these blue dots, whereas green dots are basically magnesium. So, as a result you can see the lot in both the sheets, octahedral sheet and tetrahedral sheet, the isomorphous substitution going on. As a result of that, there is lots of charge imbalance developed in this both sheet, and as a result of that high nutrient supplying charge imbalance occurs, and as a result of this charge imbalance negative charge developed. As a result of high negative charge, this vermiculite has the capacity to attract the nutrient cations, and as a result this type of soil can supply high amount of nutrients to the plants. So, if we move ahead and see the electron microscopic view of vermiculite, you will see that this is the electron microscope view of vermiculite. It has the highest cation exchange capacity because of huge amount of substitution going on in the tetrahedral sheet as well as in octahedral sheet. It has less swelling capacity than smectite, but more than kaolinite, and it is nutrient rich. Why it is nutrient rich we have already discussed, and it is stable under low pH conditions. So, another very important mineral is known as the chlorite, and the structure of the chlorite is a specific we designate the structure of the chlorite as 2:1:1 type of clay, or sometimes we call it 2:2 type of clay also. So, what are the features of chlorite? So, basically it has the 2:1 type of layer, octahedral sheet sandwich between two tetrahedral sheets, just like as any other 2:1 type of clay mineral. However, in the interlayer space is basically dominated by a hydroxide sheet. So, as you can see 2:1 type of clay with continuous hydroxide interlayer, and these iron and magnesium occupy these octahedral sheets. So, you can see these octahedral sheets are basically dominated by either iron or magnesium, And in this hydroxide octahedral sheet in the interlayer space, maybe it is a trioctahedral or it may be dioctahedral. If it is a dioctahedral, it is known as the brucite layer, where the hydroxide sheet is dominated by magnesium, whereas if it is a dioctahedral hydroxide sheet, then it is known as gibbsite. So, in the dioctahedral, it is dominated by basically aluminum. So, these are two types of hydroxide layer which can come in the interlayer space of the chloride clay mineral. Now, in the trioctahedral, I mean there is another called ditrioctahedral. So, dioctahedral in the 2:1 type of layer and trioctahedral in the interlayer octahedral hydroxide sheet. In this condition, it will be called a ditrioctahedral chloride. Another condition is trioctahedral chloride. That means, trioctahedral in the octahedral sheet of the 2:1 layer as well as the interlayer octahedral hydroxide sheet. So, both the hydroxide sheet as well as the octahedral layer will be dominated by magnesium in case of trioctahedral. However, in case of ditrioctahedral, the interlayer space will be dominated by trioctahedral hydroxides like brucite. However, in the 2:1 type of layer, the octahedral layer will be dioctahedral, that means dominated by aluminum. So, I hope now it is clear to you. So, if we move ahead and see the structure in details, obviously this shows the detailed structure of chloride. As you can see that this is the oxygen atom followed by either silicon and aluminum, because here some tetrahedral substitution is also occurring. In the octahedral sheet, either it is dominated by aluminum, then we call it as a dioctahedral. If it is dominated by magnesium, then it is a trioctahedral, and similarly when it is dominated by Fe2+, it is also trioctahedral. And in the interlayer space, it is basically occupied by this hydroxide interlayer. So, this is how this chloride structure will look like. Okay. Now, chloride shows restricted swelling due to lock interlayer structure. Since there is a magnesium or aluminum hydroxide layer in the interlayer space, it shows the lock structure, and as a result it is very nutrient poor, because there is no space for nutrients to get absorbed, and it is very common in sedimentary rocks and the soil derives from them. So, if you see a visual comparison between different types of clay minerals, it will be more clear. So, we start with the kaolinite, which is a 1:1 type of non-expanding or non-swelling. The d-axis spacing is lowest, only 0.7 nanometer, because of the presence of the strong hydrogen bonding in the interlayer space. It is also a collapse structure. And then we go to montmorillonite, where there is huge interlayer space and the isomorphous substitution occurs in the octahedral sheet, and the interlayer space is occupied by water molecules and miscellaneous cations. The d-axis spacing is highest, 1 to 2 nanometer. Vermiculite also 2:1 type of expanding, some swelling. It is not as much, it does not give as much as swelling as montmorillonite, but it also gives some amount of swelling. It is basically the interlayer space is dominated by water molecules, magnesium and other ions. The d-axis spacing is 1 to 1.5 nanometer. Similarly, illite, which is a fine grained mica, it is basically a weathered product of mica. The interlayer space is dominated by potassium, and it is showing the restricted swelling, and the d-axis spacing is only 1 nanometer. In case of 2:1 type of chloride, it is basically dominated by the hydroxide layer, hydroxide sheet in the interlayer space, giving a lock structure. So, this is a visual comparison of different types of different important clay minerals, showing their structural differences. So, if we see how this clay mineral basically develops or converts from one type of clay mineral to another type of clay mineral, we have to see this this diagram. So, this diagram basically shows how this primary mineral ultimately goes to the iron and aluminum oxide, which is the highest which is the highest form of degradation or chemical weathering or highest chemical weathering products. So, the primary minerals, first it develops to illite and then chloride, and then by removing the potassium from the interlayer space of the illite, it develops into vermiculite. And also in case of chloride, when the magnesium interlayer hydroxy interlayer sheet is removed due to weathering process, chemical weathering, it collapsed into vermiculite. And in the vermiculite, when the interlayer magnesium gets depleted, it develops into smectite, which is still it is a 2:1 type of mineral. Then the smectite goes further weathering and then remove one silica tetrahedral layer. So, there is a loss of silica and it converts into the kaolinite, which is a 1:1 type of mineral. And from there 1:1 type of kaolinite, when there is a further degradation, further chemical weathering, high intensity chemical weathering, warm and humid climate, then there will be further loss of silica. Ultimately, it will be developed into the iron aluminum oxide. So, you can see that in this direction there is an increased weathering rate. So, obviously, the illite and chloride will appear in the initial stage of weathering. However, kaolinite and iron or aluminum oxide will appear in the final or the later stages of weathering. So, guys, we have covered the basic the major important 2:1 type of mineral and 1:1 type of mineral, clay mineral in this lecture. In the next lecture, we will be talking about some other important secondary clay minerals and other secondary minerals, different intergrade mineral, interstratified mineral, and also we will be talking about different methods to identify different clay minerals. Thank you. Let us meet in the next lecture.